Okay guys, so here we're going to derive the formula for the expectation of a binomial distribution. If x follows a binomial distribution with n as the total number of trials and p be the probability of success, then probability of x is equal to r is NCR 1 minus p to the power n minus r and p to the power r. And if we recall the formula for expectation is summation probability times the random variable. So in this case, the expectation must be summation r equals 0 to n r, which is random variable, times its probability, which is NCR 1 minus p to the power n minus r and p to the power r. I can write NCR as n factorial upon r factorial into n minus r factorial. And in the next step, I can simplify n factorial as n into n minus 1 factorial and r factorial as r into r minus 1 factorial. So I realize that I can cancel r and r over here. If you look at this very closely, it's just rewriting of n minus r. So n minus 1 minus r minus 1 is same as n minus r. I've also splitted p to the power r as p times p to the power r minus 1. And the next step, I can take n and p outside the summation sign because they are not function of r. And I can rewrite n minus 1 factorial upon r minus 1 factorial n minus 1 minus r minus 1 factorial as n minus 1 c r minus 1. The rest I've copied as it is. So if you look at the summation term, you'd identify that this is a binomial expansion of a, which is 1 minus p, b, which is p to the whole power n minus 1. So I can write it down as 1 minus p plus p to the power n minus 1, which simplifies as 1 to the power n minus 1 or 1. So hence the final answer of expectation that I get is n times p. Okay guys, so next up we're going to see how to derive the formula for the variance of x. To find the variance of x, we need to find out the expectation of x square. So an expectation of x square would be a summation of all the terms of r square multiplied by the corresponding probability. So hence it should be sigma r equals 0 to n r square NCR 1 minus p to the power n minus r and p to the power r. I can open NCR as n factorial upon r factorial into n minus r factorial. And then I can write n factorial as n into n minus 1 factorial and r factorial as r into r minus 1 factorial. And I can also rewrite n minus r factorial as n minus 1 minus r minus 1 factorial. So if you'd simplify this, you'd see that this is same as n minus r factorial. I can cancel one of the factors of r over here. So it simplifies as r into n. And if I look at this closely, n minus 1 factorial upon r minus 1 factorial times n minus 1 minus r minus 1 factorial, that is same as n minus 1 c r minus 1. So guys, in the next step, I can rewrite r as r minus 1 plus 1, which is same as r. And hence I can split it up as r minus 1 and another term of 1. So I've written the entire thing down with the factor of r minus 1, and I've written the entire thing down with the factor of 1. We can take n outside because it is not a function of r. And in the next step, I can write down n minus 1 c r minus 1 is n minus 1 factorial upon r minus 1 factorial times n minus 1 minus r minus 1 factorial. The rest of the factors are being copied as it is. I can rewrite n minus 1 factorial as n minus 1 into n minus 2 factorial, and I can rewrite r minus 1 factorial as r minus 1 into r minus 2 factorial. I have rewritten n minus 1 minus r minus 1 as n minus 2 minus r minus 2, which is pretty much the same thing. I've also split it p to the power r as p to the power r minus 2 times p squared. And in the second term, I have split it p to the power r as p to the power r minus 1 times p. From the first term, I can take n minus 1 and p square outside the summation sign because they are not functions of r. And from the second term, I can take p outside the summation sign because that also is not a function of r. And hence I can write down n minus 2 factorial upon r minus 2 factorial times n minus 2 minus r minus 2 factorial as n minus 2 c r minus 2. Now if you look at the summation term, you would see that this entire summation is actually a binomial expansion of first term 1 minus p, second term p, and whole power n minus 1. So it becomes 1 minus p plus p to the power n minus 1. In other words, if you will expand this entire thing with first term as 1 minus p and the second term as p, you will get the same series as in the previous step. Likewise, if you look at this particular term, likewise if you look at this series of terms, you would identify that this is a binomial expansion of 1 minus p plus p to the power n minus 1. 1 minus p plus p simplifies as 1 and 1 to the power n minus 1 simplifies as 1. So I can write down the first term as n minus 1 p square and the second term as n into p. Taking np common from all the three terms, I get np times np minus p plus 1. Now that's the expectation of x squared. To find out the variance, I'm going to use the formula expectation of x squared minus expectation of x whole square. Expectation of x squared is something that we've just found out, and we found the expectation of x earlier on as np. So square of expectation of x would be np square, np whole square, that's n square p square. When I open and simplify, the n square p square term cancels out, and if I take np common, it becomes np times 1 minus p. 1 minus p is equal to q, and hence the variance of a binomial distribution is npq.